Hey physics. Um, this is a little quick explanation for the projectile motion lab, in which we basically kicked a soccer ball around, right? The soccer ball became a projectile, and what the graph that you see here, right, the title, is change in distance in meters versus time in seconds. And what you should see is there's a linear fit, there's a best fit line for this information, and there's a best fit curve for this other information. Something is circled down here. What you'll also see is there's some math down here, which I'm going to explain. I swear, right? I'm gonna talk you through the process of what we did during class. So, basically, what I asked them to do during class in groups is to take a soccer ball, kick it in the air, and take a video of the ball, right? Track it as it flies through the air, and determine, right? Compare. Our purpose, the official purpose, was to compare the theoretical distance to the actual, the measured distance in real life, right? In theory, based on calculations from a graph, the ball should go a certain distance. In reality, right, the measured distance is going to be slightly different, and the difference between those can be explained by, a number of factors, possibly some errors when tracking the object, possibly air resistance, possibly an angle of the camera, but that's something for you to kind of talk about in the analysis, where the calculations in the real life scenario, why wouldn't they match up perfectly, right? So what the groups did was they kicked the ball, they recorded a video, they threw the video into Logger Pro and tracked the ball as it boop, 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 went through the air, and each of these dots corresponds to its position, right? This is not in color, so it's not a perfect representation, but just imagine, if you will, that the dots that I'm mousing over right now, right, are a certain color, so they represent the x direction. And that's why this is a linear fit video analysis for the x information. It's a linear fit because projectiles in the x direction have zero acceleration. Because they have zero acceleration, you can log distance versus time as a straight line, as velocity. Right? Should also see that there are other points here that are connected by a curved fit. So this is auto fit for a video analysis Y, and I can zoom in on that a little bit. So auto fit for video analysis Y, and then it's in the form AT squared plus BT plus C. And that should sound kind of familiar, should look kind of familiar, and there is a reason that this B value is circled, right? AX squared plus BX plus C is the general formula for any parabola, but specifically in our case, 1/2 AT squared plus VIT plus initial position, right? That's the big equation. I've kind of flipped it around a little bit, but that's the big equation. There we go. As far as the linear fit is concerned, x equals mt plus b. Well, this is y equals mx plus b, right? That's the generic formula for a line, as far as math is concerned. Physics-wise, final position equals VIT, initial velocity times time, plus initial position, right? This is the position formula. This is initial position, this is the basic velocity formula. Let me see. I think I have the reference table, so hang on. Let me pull up yeah, no, there it is, physics reference table. So I'm going to bring it over. If I go and I look right here, this is the big equation, right? And the big equation, all I did, the only difference is that this is oh gosh, don't highlight the whole thing. This term right here, this is AT squared. This term right here is BT. And I said this was delta, the change in position, change in distance, which means it's final minus initial. So the initial position to go on the other side. And that is why, looking at this, right, AT squared, right? Well, 1/2 AT squared. So 1/2 A here in our formula is the same thing as a on this formula. Now that's not what we're worried about. We're worried about the velocity. Now I'm going to tell you why we need the velocity in a second, but that's why this b value is circled, because this b value represents the initial velocity. Look, it's b times time. And looking at our formula, vi is the initial velocity times the time. So we need this b value for something. And then we need this slope, because the slope is y equals mx plus b, but it's also x final equals velocity times time plus initial position. This is an expansion, I think I had you write this on yours, of this equation, where this is really v equals delta d over t. So multiply both sides by t for time. I get that velocity times time equals change in position, delta d. Delta anything, like we talked about last year, it was final minus initial. So vt equals x, or final distance minus initial distance. Move initial distance over. Final distance is velocity times time plus initial distance. So that's where this m, the slope, and you look, the units are in meters per second, so this is very clearly a velocity. This is the x velocity. This is the y velocity. And the reason we need both of those is that we need the x and y velocity in order to do a projectile motion question. If I want to figure out how far something is going to go, I need to know how long it's in the air. If I want to know how long it's in the air, I need to know how fast it's going up, so that I know how long gravity will have to work against it before it stops it. Now, what? Hello? Why are we? There we go. So our purpose was compare the theoretical distance of the projectile to the measured distance of the projectile. And y'all should be getting an email soon with the this file, this actual picture file, and the actual distance that it traveled for this particular graph. Right. Now this y equals mx plus b, and y equals ax squared plus bx plus c. The slope was the velocity, so this m was the velocity. And here is that relationship, right? Final distance is 1/2 at squared plus vit plus initial distance, which is why this b value corresponds to the initial velocity. Now, what we have, right? And what we have is right here. The initial x velocity is equal to the slope. The initial y velocity is equal to the b value from the graph. And again, I'm taking this b value without the plus minus. The plus minus has to do with how well do your graph points fit this line, or fit this curve. So don't worry about the plus minus. We'll assume that it's a pretty good fit. It's pretty good, less than half. That's a less than 10% difference. But here's the b value. So this many meters per second is the y component. All right. I know the acceleration in the x direction is 0. I know the acceleration in the y direction is the acceleration due to gravity, negative 9.81 meters per second squared. I know the initial x position and the initial y position are both 0. I'm looking for how far did it go. That's what I'm going to try to figure out, right here. So I need the time, right? X direction, I need the time. Otherwise, and then I can solve. The y direction, this person already solved, so I want you to solve it for yourself, even though they've already solved it, so let's ignore that for a second. But in the y direction, I know that it starts here, and I know that eventually this thing is going up, the soccer ball is going up, eventually it has to come down. In between going up and going down, it has to stop. So at the peak, it will stop. So I know the final velocity is 0. So I can use my initial velocity from the graph. I can use my acceleration. I can use my final velocity to solve for a time. And that's what we've done here. Right? And again, do this on your own. But here's the basic form. And again, I know that I'm giving this to you. I know that I'm showing you this. I do want you to do the calculations on your own, even though they might be in front of you, because one, it's good practice. Two, I do want you all to show me that you can do it. Not that I don't trust that you can do it, but show me in the lab, right? So here is the part of the equation that you need. Final velocity is initial velocity plus a times t. You know the acceleration. This is the value from the graph right here, this b equals 0. So you can solve for t. Now, that is the time it takes to get to the top. If I want the time it takes to go the whole way, I need to double it. So whatever time you solve for here, you have to double it. And then you can plug it into this equation. right? And when you plug it into this equation to find the final horizontal distance, you're looking for the final horizontal distance. The acceleration horizontally, we established, was 0. So this is 0. The time is twice the time it takes to go up, because again, it has to go up and down, right? In the y direction, it's just doing this. In the x direction, it's doing this. So combined, it goes like this. So if I'm calculating this time, I need to double it so I can get all the way back down. So this time is 2, but again, because the acceleration is 0, that part won't matter. This velocity is the b value from the graph times time. Again, double the time that you just solved for. And the initial distance is 0. Right, so this is your theoretical distance traveled. Your actual measured value of the distance traveled will be in the email. I'll tell you what, specifically for this graph, how far did the ball actually go. So I'll show you that. But that's your purpose. Your purpose for this lab was to compare the theoretical, what according to these numbers, how far should the ball have gone, compare that value to the actual measured. We took basically a measuring tape and measured from the distance from the point that it was kicked to the point that it landed back on the ground, what that actual distance was. That's your purpose. Compare those two things and explain any discrepancies, right? Now, again, could be like air resistance, could be a matter of how did we graph this, could be a matter of was the angle of the camera correct. There are a number of reasons. Do your best to explain them within reason. You don't have to go over the top and explain every single little thing, but do your best to explain it to the best of your abilities. All right. Now, another video will go up because there is a second lab to go through. It's momentum. It's a little more tedious. There are more graphs to look at, and I will explain that in a separate video. But this will give you a decent start for the projectile motion review lab. If you have questions, please email me. Otherwise, I'll see you in the next video. Take care.